Hello learners, welcome to the next video. So in this session we learn about the semiconductor materials. So semiconductors, as we know, they are used in electronics. So to understand why semiconductors are used in electronics, let's first see the classification of materials. Okay, so these are the material classifications on the basis of its conductivity. Okay, on the basis of the conductivity, we know the materials are classified into three types: conductors, semiconductors, and insulator. Okay, so as we know, conductors will have the maximum conductivity, right? The conductivity means how the material is conducting electricity is called as conductivity. How they are giving the flow of current, how the flow of current is there. If the flow of current is maximum or more, then we say the conductivity is good. If the flow of current is less, if the flow of charges is less, then we say conductivity of the electricity is less. So the conductivity is measured in Siemens per meter. Siemens per meter. So the conductors will have very good conductivity, right? So whenever the voltage is applied, the conductors allow the good amount of charge to flow. We can take the example copper, silver, aluminium, gold. Okay, this will conduct the electricity. This will this will conduct, this will have good conductivity, I can say. Okay, the coppers conductivity is up to 10 power 7 Siemens per meter. So on the other hand, if we see the insulators, we can say it hardly allows any flow of charge. There is no flow of charge at all. Best examples are wood, glass, Teflon. Okay, minimal charge. So when we take the example of wood, the wood's conductivity is 10 power minus 14 Siemens per meter. Right? Now, when we take the case of semiconductors, its conductivity is between the conductors and insulators. Whenever the voltage is applied to the semiconductor, then it allows a moderate amount of current when by adding some impurities. Okay, when we add some impurities, the conductivity of the semiconductor can be changed, it can be increased. So for this purpose only, we are using the semiconductors for designing in the electronic devices. Understood? The semiconductors conductivity is between conductors and insulators. The semiconductor's conductivity can be controlled by using the impurities or by adding the impurities, by doing some external, there are some external factors with which the semiconductor's conductivity can be controlled. Okay, for this purpose only we are using semiconductors in many electronic devices. Examples are silicon, germanium, gallium arsenide. Okay, so let's understand by taking the example of silicon, what is happening inside the semiconductor, what is the bond formation. Okay, all that we'll see. Now when we take the silicon, we know silicon atomic structure, right? That the atomic number of silicon is 14. That means it has 14 protons, 14 electrons. 14 protons inside the nucleus and 14 electrons are revolving around the nucleus, right? Like this. So this is a silicon nucleus. 1 2 3 4 5 6 7 8, right? 8 9 10 14, no, 11 12 13 and 14. So what is the outermost orbit? The number of electrons in the outermost orbit is how much? 4. Okay, 1 2 3 4. That means we can say there are 4 valence electrons. The outermost orbit has 4 electrons. So that is nothing but there are 4 electrons, right? So we can say the silicon has 4 valence electrons. So whenever silicon combines to form a solid, or when it is arranged in a particular pattern, let's say crystal structure, each atom will share its, like when we say 1 2 3 4 in the outermost, no? So this will share its outermost, these two atoms, the silicon atom and this silicon atom will share its outermost electrons with each other, forming the covalent bond. Now if another silicon atom is here, so one electron here and one electrons of this will share with each other to become stable and thus forms covalent bond. Now at the temperature just above 0 degree Kelvin, due to thermal energy, now, let's see this silicon atoms diagram. See here, silicon atom forming covalent bond, right? You can see 1 2 3 4 electrons in the outermost orbit, and the next atom, the nearest atom also will have 4. Okay, not only single atom, no, there are many atoms. So each atom will have 4 outermost electrons, 4 valence electrons, and the 4 valence electrons are being shared like this, which is called as covalent bond. Okay, here covalent bond formation is happening. Now what happens? Okay, in such a way you will have many like this. Okay, by forming the covalent bond, right? Right. Now when at the temperature just above 0 degree Kelvin, because of the thermal agitation, as the thermal energy is increased, what happens to the silicon crystal? The silicon crystal the atoms in the silicon crystal will start vibrate, and due to that vibrations, some of the electrons will get a minimum energy, enough energy that it can break this covalent bond and it can move freely. Okay, the electron will break from the bond, and the electron will act as a free electron. It will move around. So at the room temperature you will find many such free electrons in the silicon structure. Now whenever this electron departs from its position, now let's see, I'll show you the, see, I'll show you the diagram. So as we have seen, this is a covalent bond formation, right? So silicon's outermost orbit will have 4 electrons, right? And this silicon atom will have another 4 electrons in its outermost, and this will have 4. Okay, by this form of sharing, or by this type of sharing, the covalent bond formation is happening. Okay, so now at the room at the temperature little above the 0 degree Kelvin, because of this thermal agitation, the silicon crystal, what it does, the atoms in the silicon crystal will vibrate, and due to that vibration, that means the electrons is getting energy, no? Because of that energy, it will break this covalent bond and it will move around. Okay, you will find many such free electrons at the room temperature. So whenever the electrons, so see here, whenever the electron from here has jumped here, what happened here? Here the hole is created. Okay, the vacancy is created here. The vacancy is created. Now here was an electron. Due to the energy it gets, it had jumped here. So this is now called as free electron, okay, or conduction electron. Okay, now what happened here? Because this electron departed from here to here, here a vacancy is created. Okay, that vacancy is known as hole, valence hole. Okay, and this vacancy is known as a hole, and this will have the positive charge. Okay, the hole will have a positive charge. Similarly, as like electron is having a negative charge of magnitude 1.6 into 10 to the power of minus 19 coulomb, it will have plus 1.6 into 10 to the power of minus 19 coulomb. Okay, valence hole will have positive charge, electrons are having negative charges, as we know. So by not having an electron at a particular position, a hole is created. a vacancy is created, and that vacancy is called as hole. So what does this hole do? This hole will attract other free electron. Okay, it will attract other free electron. Now what happens here? Here hole is formed, and this hole will attract another electron. Like that, you will see the electrons and holes recombining, or you can say electron hole generation is happening. Electron gets recombined with the holes. So what can we say about the number of electrons and number of holes here? Obviously, the number of electrons will be equal to number of holes, isn't it? As the electrons are moving, hole is created. As the electron is moving, hole is created here. Right? In this way, we can say the number of electrons is equal to the number of holes. So here we can say in semiconductors, we get a flow of current due to the two types of charges. What are they? Electrons and holes. Because as in the case of conductors, the conductivity is only due to electrons. But here in the semiconductor, the conductivity is due to two charges. What are they? They are electrons and holes. Now this semiconductor again can be classified into two types. Okay. Semiconductors again classified into two types, extrinsic and intrinsic semiconductor. Now what is intrinsic semiconductor? So intrinsic semiconductor is a pure form of semiconductor where no impurity is added. Now what is impurity? How can that be added? We will see here. So let's first see, a pure semiconductor is called as intrinsic semiconductor. Okay, I will show you. No, yes. So this is a pure form of semiconductor. Okay, this is a pure form of semiconductor where the silicon atom has a neighboring atom as a silicon only. It has a silicon atom only. There is a silicon structure, silicon crystal structure, where the silicon atoms can only be seen. All are silicon atoms only, forming the covalent bond by sharing its 4 outermost electron to the other 4 outermost electron of like other neighboring atoms, right? In this way. So this can be said as intrinsic, pure form of semiconductor where no impurity is added. Now, whereas extrinsic semiconductor says that extrinsic. Now extrinsic is also again of two types. Extrinsic semiconductor is of two types. P type, right, and N type. P type and N type semiconductor. Now, when it is called as P type, when it is called as N type, this is due to the impurity. Okay, due to the impurity that is being added, we classify extrinsic semiconductor as P type and N type. Now, when we see in the periodic table, you see the fourth group elements will have the semiconductors, like silicon, germanium. Okay, these are the semiconductors. And 5A group elements, here are the 3A group elements, right? Boron, aluminium. Now 5 elements are phosphorus, arsenic, when we take these two examples. Now here for the silicon atom, we are adding 5A group element. Like we are adding phosphorus here. We are adding phosphorus. Now how many electrons, how many valence electron does the phosphorus have? In its outermost electron, the phosphorus will have 5 electrons, right? In its outermost orbit, the phosphorus has 5 electrons. 1, 2, 3, 4, 5, right? Okay? 5. Okay. The phosphorus, when added to the silicon as an impurity, as it has 5 outermost electrons or valence electrons, the 4 will be shared by the nearest silicon atom. The 4 will be shared by the nearest silicon atom. So this is being shared with this is being shared with this atom, this electron, this being shared with this electron, and this being shared with this electron of silicon and phosphorus are being shared. They are sharing their electrons in this way. But phosphorus will have another electron remaining, right? We can see here an electron is left out here. Okay, an electron is left out here. Okay, by this way, when we are adding many number of impurities, phosphorus as an impurity, when we are adding to the when we are adding to the silicon, what happens? The structure is remained with many of the free electrons like this. Yes or no? So we are adding the impurity to the external impurities are added to change the conductivity of the semiconductor, right? So this pentavalent impurity is added to the pure semiconductor. Then such a type of semiconductor is called as N-type semiconductor. Okay, when pentavalent is added. So what are more? Because as electrons are remaining, electrons are being left out, the electrons are in majority. Electrons are in majority, holes are in minority. Similarly, when boron as an impurity is added to the silicon, that means when 3A group elements, which are known as trivalent group elements, right, which are known as trivalent atoms. So when these trivalent atoms are added, you can see here, so this is the outermost electron of boron, this one is the outermost electron, and this one is the outermost electron. This will form the covalent bond with the silicon, this will form the covalent bond with the silicon electron, and this will form the covalent bond with the silicon. Okay, now what is remaining? One silicon atom's outermost electron is left alone. That means a hole is created here. That means a holes will be more. Holes are left out. No? Okay, so here the holes are in majority. Holes are in majority and the electrons are in minority. Understood the concept? So this process of adding the impurity to the semiconductor is called as doping. Okay, when we are adding the impurities, which impurities? Either trivalent impurity or pentavalent impurity we are adding to the semiconductor. So this process of adding impurity is called as doping, and the atom which is being added as an impurity is called as dopant. Okay, dopant. So when we add pentavalent impurity, it forms N-type semiconductor. When we add a trivalent atom, it forms a P-type semiconductor. Right? The example of pentavalent are phosphorus, arsenic, and trivalent atoms examples are boron, aluminium, gallium. Okay? So this is about the intrinsic and extrinsic semiconductor. We'll see. Okay, what happened in the intrinsic semiconductor? No impurity is added. It's a pure form of semiconductor. Only silicon atoms are present. So equal number of electrons, equal number of holes. No external impurity. For the extrinsic semiconductor, it is doped with impurity either with trivalent or with pentavalent atoms. Why we are adding? To control the conductivity. Okay, to enhance the electrical properties, we are adding the impurity, so that we can use them in a electronic devices, right? So again, the extrinsic semiconductors are of two types, p type and n type semiconductor. When it is called p type, when it is called n type? When the holes are in excess. That means when will the holes be in majority? The holes are in majority when trivalent impurity is added. Okay, N type is, the semiconductor is called N type when pentavalent is added and when electrons are in majority. Okay. P type. Trivalent dopant is added. Right? What I said was okay. Yeah. Trivalent. P type semiconductor means trivalent dopant is added like boron, aluminum, gallium. Okay. Third group elements. 3 valence electrons creates holes. 1 vacance remains in outer orbit. So excess holes are generated. Majority are holes. So as the holes are attracting the electrons, they are attracting the electron towards them. They are called as acceptor atoms. Each hole can accept one free electron. Coming to N type, when pentavalent dopant is added, that type of semiconductor is called as N type semiconductor. Here 5 valence electrons are there in pentavalent atom. So what is created? Free electrons are created. Okay, excess electrons are there. Majority are electrons, minority are holes. Holes are in minority. So they are called as donor atoms. Okay, they are called as donor atom. Each atom will donate one free electron because one free electron is left out now, so they will donate. That is why it is called donor atom. Okay, P type majority are holes, minority are electrons. N type majority are electrons, minority are holes. Remember. Okay, N type means majority are electrons. Okay, understood the class? We have seen the silicon structure. Okay, with 4 valence electrons. They are sharing their outermost electrons with each neighboring atoms of the silicon, and they are forming the covalent bond. So in that way, electrons, number of electrons will be equal to number of holes, which is called as pure form of semiconductor or intrinsic semiconductor. Okay, both electrons are and holes conduct current in the semiconductors, unlike the conductors. In the conductors, only electrons will create the electricity or will conduct, but in semiconductors both electrons and holes are creating the or conducting the current. Doping process, the process of adding impurity to the pure form of semiconductor. The process of adding impurities to the pure semiconductor is called as doping, and the impurity is called as dopant. Impurity which is being added is called as dopant. Okay. Impurities control. Why we are adding? We are adding to control the conductivity of the semiconductor. So there are many applications in the devices with these semiconductors where we can control its conductivity. Okay. So understanding p-type and n-type semiconductor is essential for designing modern electronic devices. So I hope you understood what we have learned. We have just seen when we go through. We have seen the semiconductors, the bond formation, and intrinsic, extrinsic semiconductors, and in extrinsic again they are p-type and n-type. Okay. Materials are of 3 types: semiconductors, conductors, and insulators. Learning about semiconductors. Semiconductors will have the conduction due to electrons and holes. Okay, we have seen the silicon atomic structure. It will have the covalent bond formation. Okay, how they are formed you can see in the diagram. So electron hole pair generation is there. So some few lines about free electrons. They are negatively charged, having the magnitude 1.6 into 10 power minus 19 coulomb. Holes will have positive charge with the same magnitude. What does the free electron do? They break the free covalent bonds because of the thermal agitation. Holes means vacancy that are created due to electrons departure. Free electrons move freely through crystal. What about the holes? Holes will attract the nearby electrons. Okay. Now there are 2 types of semiconductors. What are they? Intrinsic and extrinsic semiconductor. Intrinsic means intrinsic is a pure form of semiconductor. Okay, pure form of semiconductor. Pure form of semiconductor is called intrinsic, and impure form of semiconductor is called impurity. If impurity is added, then it is extrinsic. Now extrinsic again divided into, classified into p type and n type. Okay, P type and N type. You can see intrinsic pure form, all atoms are silicon atoms only. Number of holes is equal to number of electrons. Now extrinsic, as we said, P type and N type. A semiconductor is called P type when trivalent dopant is added, where excess holes will be generated. Okay, an N type semiconductor is called N type when pentavalent dopant is added. Here the excess are majority are electrons here, minority are holes here. Okay, P type and N type. So that's it about today's class. I hope you understood. Let's meet in the next session. Thank you.